In this subsection, we'll discuss how sensors and filters respond to harmonic inputs. And we'll begin by talking about sensors. So we're talking about sensors in a general way. I'm going to define it for this course as a sensor being something that's converting a measurement of one type into typically a voltage reading. This is if we're talking about an analog sensor, but digital sensor would have a similar type of response where we are measuring some typically physical quantity and then we get a voltage reading depending on the value of that physical quantity. So typical examples you've probably dealt with before. We've used thermocouples to measure the temperature, accelerometers to measure acceleration. We can use an ultrasonic sensor to measure position. And at least the first two of these are often going to be analog measurements. So the voltage we're reading is going to be dependent on the temperature that the thermocouple is sensing, or the acceleration that the accelerometer is sensing. But we can have all types of other sensors as well to measure various quantities. Now again, these sensors are taking some input and then making some output. So they themselves are going to be a transfer function. The input is the quantity they're measuring, again like temperature or acceleration, and then it goes through the sensor and gives some output based on that input that we read typically as a voltage. So the sensors themselves could be a first order system, a second order system, higher order. It all depends on how it is converting the physical quantity into a voltage. And because it's going through this transfer function, the quantity that we're reading, the physical quantity we're reading, and then the voltage that we're getting out of it might be different. There could be a time delay as the sensor is getting like up to temperature if we're talking about a thermocouple. And we're going to see on the next slide that it is going to also depend on how frequently the input is changing what we're seeing in the output. But we can see that like for a thermocouple, it's going to take time for the thermocouple, if, let's say it's immersed in a liquid, it's going to take time for that thermocouple to come up to temperature and give us the correct reading. Or if the liquid is cooling, it's going to take time for it to dissipate its heat and give us the correct reading. It doesn't instantly give us the correct value. And if we're working with another type of sensor like an accelerometer, it has an actual very small cantilever beam in it. So what the accelerometer it's sensing is going to be dependent on how fast that beam is going to be vibrating. But the beam itself has this inertia that it has to overcome. It's not going to give us this instantaneous reading of the physical quantity. Where sensors fit in with what we've discussed before when we were looking at the state space modeling, where we came up with our matrices, the A, the B, the C, the D matrices, the sensors are really coming in when we're talking about that C matrix. The C matrix is giving us what I was referring to as the observables of our system. These are the actual quantities we are able to measure as the system is moving. So as opposed to the A matrix, which puts together how the physics of the system work together. So in like a mechanical system, our A matrix might have been comprised of positions and velocities, but we saw in the C matrix, often we were only sensing positions. So the C matrix is all based on the sensors that we have. If we have like ultrasonic position sensors in our system, or maybe a transducer, then maybe we can be measuring directly the position of our different objects, but we don't have a way of directly measuring the velocities. Now the position and the velocity are related through the time derivative, so in theory we could numerically differentiate the position information and get that, but we are only going to be directly sensing what the positions of our quantities are. And this comes into play as we get into also controllability, which will be outside the scope of this course, but depending on the quantities we are able to directly measure in that C matrix is going to determine how we can control the system as well. Now the sensors, the output of the sensor is going to depend on, well, the transfer function of the sensor itself, how long it takes to be able to get a reading, and that's going to influence what we call the sensor range. So first a little bit more on how typically an analog sensor is going to work for us. We're going to have to start by doing some sort of calibration routine for the sensor, because really what we are interested in is how does the physical quantity we're measuring pair with the voltage reading that we are getting. So a calibration routine could be something like, again, let's take a thermocouple, for example. We could put our thermocouple into ice water where we have a known temperature. We know it has to be 0 degrees Celsius, and we can take the voltage reading at that point. Then we can put our sensor, our thermocouple, into boiling water. We know that's 100 degrees C, at least at sea level. So we have a voltage reading at that temperature. And then in that range, if it's a good thermocouple, we should have a linear change in voltage that corresponds to the linear change in temperature. Now, we probably to calibrate it better would take it at other known points as well to get a better fit. But what we're trying to establish is the linear relationship between the quantity it's measuring and the voltage. So that way later, when we're getting a voltage reading off of it, we know how to translate that into what is the value of the quantity it measures. A lot of times these calibrations are done statically, so we have our water at a constant 0 degrees. We take our measurement, so we give the thermocouple time to get down to that temperature, or we immerse it in the boiling water, we give it time to get up to that temperature, and we get that reading. And so the sensors we often are going to treat as ideal in situations where two things are going to be happening here. In an ideal sensor, it's sensitive only to the property it's measuring. So in the case of a thermocouple, we want the voltage that we're reading it to change only based on the temperature that the thermocouple is experiencing and no other quantities. So for a thermocouple, that's great. If the voltage changes with temperature, that is the whole idea. However, if we're dealing with something like an accelerometer, where its job is to be measuring acceleration, accelerometers are often prone to changes in voltage also due to temperature. So if its job is to measure acceleration, but it's experiencing a temperature change, which is changing the voltage reading, that is not great for us because we're not trying to measure temperature with the accelerometer, only acceleration. So in an ideal sensor, that's not the case. It only is going to change based on the desired quantity we want to measure. And the other thing about an ideal sensor is going to be that the sensor doesn't influence the property it's trying to measure. So for example, if we have an accelerometer on, let's say it's some small object, well, the accelerometer itself is going to have mass. So if we're putting some mass on a small object, we're changing the actual behavior of the object that we're trying to measure because we're adding some inertia to it, and we're going to be influencing then what the accelerations are, what the oscillations are, maybe the natural frequencies of the object itself that we're trying to be calculating. And back to talking about sensors and how they are measuring the desired quantity, a sensor is going to have this dynamic error when the property we're trying to measure is changing quickly. So going back and talking about the calibration, again, typically we are immersing it for a while at 0 degrees, immersing it for a while at 100 degrees in the case of the thermocouple, but we might be measuring some liquid whose temperature is changing relatively rapidly. So this is now putting into the thermocouple or into our sensor a dynamically changing property. So now what we're going to be concerned with is not how good necessarily is the sensor at calculating or determining a static quantity, but something that's changing in time. And this is where the transfer function of the sensor itself is going to come into play. Because there's going to be, depending on the transfer function, it might be good at measuring low frequency changes, or it might be better at sensing high frequency changes, or maybe something in between. So we can visualize this using a Bode plot of the transfer function. And this is going to tell us, is this sensor better for low frequency application, high frequency application, or some mid frequency application. So let's demonstrate this with a couple of quick examples of looking at sensors. All right, so we have some sensor. I'm not going to show its particular transfer function, but let's say we know its transfer function, how it goes from the input quantity to the output voltage, and we plot that transfer function's Bode diagram as we see on the right here. So if we look at the shape of this Bode diagram, it looks like it's from a second order system, kind of typical of what we've been seeing for our second order systems before. we see that it peaks around 1 radian per second. So probably the natural frequency or the resonant frequency is about 1 radian per second. And as we go to the left of that, we have this pretty flat area on the Bode diagram. And you can see by the point there, it looks to be a pretty constant negative 22 decibels of gain or of magnitude. And if we go down to the phase diagram, it's about 0 degrees also in that range. So if we say that that range is, let's assume it's everything to the left of 10 to the negative 2 is also flat. As long as we are around, let's say, about 3 times 10 to the negative 1 radians per second of frequency, it's pretty much flat. The magnitude is constant and the phase is near 0. And over here, again, if we have less than about 0.1 radians per second, we'll call it. So the idea is that if we have a constant magnitude, once we do that calibration, we know the relationship between the quantity we're sensing and the voltage that we're reading. So the problem in a sensor like this is that for higher frequency inputs where our omega is higher, let's say above 0.1 radian per second or even higher than that, looking at the Bode diagram, the magnitude is now changing, and it's changing constantly. It goes up and then it starts to go down as we get into very high frequency applications. So the problem becomes that the magnitude is now not constant. So that calibration we did earlier is not going to be any good because the voltage that we're reading no longer is corresponding the same way to the quantity that we're measuring. And on top of that, in this sensor, if we look at the phase diagram, when we're above, let's say, 0.1 radians per second, now the phase starts to rapidly change. It goes from about 0, it does a quick change, and now we get into antiphase. We get down to a negative 180. So in that range where it's rapidly changing, now the quantity that we're sensing has this time delay, and that time delay gets further and further down as the phase gets to negative 180. So the voltage we're reading, it has a time delay versus the quantity that we're reading. So all of this being said, based on the Bode diagram, for a good sensor in its applicable range, we want magnitude to be flat, phase to be flat, ideally 0, but at least flat. So we would say that if our sensor's Bode diagram looked like this, we would say it's good for low frequency applications. And specifically here, let's say applications where the quantity we're measuring is changing very slowly, less than maybe 0.1 radians per second. Above that, our sensor is not going to be reliable. The readings we're getting out cannot be easily converted back to the quantity that we're measuring. But let's look at a different sensor. Again, we won't look at the transfer function, but let's say that if we make the Bode diagram, it looks like this. So the magnitude goes low and keeps dropping at low frequencies. On the other side, for high frequencies, it's also low and keeps dropping the higher the frequency is. And then we have this flat spot in the middle. The phase diagram also looks a little bit different than things we've seen before. But again, if we look between, let's say, 2,000 and 10,000 radians per second, the phase is fairly close to 0 in that range. And if we look at the magnitude, again, between 2,000 and 10,000 radians per second, the magnitude is flat at that negative 0.1 decibels. So this sensor, if we have a low frequency application, we don't necessarily know exactly how the magnitude is going to relate. So it's not going to be good for low frequency applications. And we have the same problem for high frequency applications. The magnitude keeps changing as the frequency changes. However, if we're trying to sense a quantity in this example that is oscillating between 2,000 and 10,000 radians per second, our magnitude is flat, our phase is pretty close to 0, our sensor is going to be reliable in this range. So this is, for lack of a better term, I would say that this sensor is good for medium frequency applications, but more specifically, as long as we know the quantity we're measuring is changing or has a frequency between 2,000 and 10,000 radians per second, then this sensor would be a good use in that application.